Hey everyone, welcome back to the channel. In this masterclass we are doing a complete, from the ground up deep dive into wrapper classes, autoboxing and unboxing. By the end of this video you'll understand it well enough to use it confidently in production and explain it clearly in an interview. If that sounds good, make sure you are subscribed and let's get started. Java is unusual among major languages in that it draws a hard line between two completely separate categories of types. Every wrapper class, every autoboxing quirk, and every performance trap we will discuss today traces directly back to this split. Get this foundation solid, and everything else snaps into place. Java has exactly 8 primitive types. They are not objects. When you declare an int local variable, the CPU register or stack slot holds the actual bits of that number. There is no pointer, no object header, no garbage collector metadata. That directness is why primitives are fast, but it also means they cannot participate in parts of the language that require objects, like collections and generics. A reference type variable does not hold the object itself, it holds a reference, essentially a managed pointer, to an object living on the heap. Every object carries overhead, typically 12 to 16 bytes of header on a modern JVM before you even store a single field. That overhead is the price of participating in the full Java object model, including nullability, generics, and polymorphism. Quick pause. If this is useful so far, drop a like, subscribe for a new masterclass every week, and share it with a teammate who would find it useful. Now, back to it. When you write int x equals 42, the value 42 lives directly in the stack slot, no indirection. When you write integer ref, the stack slot holds a reference that points to a heap allocated integer object. That object wraps the same number 42 but also carries a 16-byte object header. This difference in memory layout is the root cause of every performance and identity comparison issue we will examine. This is the trap that bites developers who forget the split. With primitive int, the double equals operator compares values always. With integer objects, double equals compares references. Are these two variables pointing at the exact same object on the heap? They are not, so the result is false. The equals method restores value semantics. Always use equals when comparing wrapper objects. This dual-type system was a deliberate pragmatic choice by Java's designers. Pure object-oriented languages like Smalltalk treat everything as an object, but that comes at a significant runtime cost. Java kept primitives for raw computational speed and chose to bridge the gap with wrapper classes wherever the object model is required. Project Valhalla, currently in preview, is the long-running JVM effort to eventually unify these two worlds with value types, but for now, the split is very much alive and you must understand it. Java's type system is divided into two worlds, primitives and objects. That division creates a very real problem when you need to store primitives in collections or pass them as generic type arguments. Wrapper classes are the bridge, and autoboxing is the mechanism that makes crossing that bridge feel invisible until it isn't. Primitive types are value types. Declaring an int gives you a variable that holds the integer bits directly. There is no object wrapper around them, no heap allocation, and no pointer to follow. This is why primitive access is as fast as it gets, one address, one read, done. That inline storage also means a class with 10 int field space, no per field allocation overhead beyond the bits themselves. Whether a primitive is a local variable or an instance field, the bits live exactly where the variable is declared, no heap allocation, no header, no pointer. A point with 2 int fields costs exactly the object header plus 8 bytes of data. There is nowhere cheaper to store numeric data in Java. A primitive variable holds the value itself, no indirection. A reference variable holds a memory address pointing to an object on the heap. That heap object carries a JVM header, typically 12 bytes on a 64-bit JVM with compressed oops before any actual data begins. For string, the data is a char array, which is itself another heap object with its own header, so two allocations and two pointer hops separate you from the characters. When you declare a reference type variable, you get a slot that stores a pointer, not the object's data. The actual object lives on the heap and always begins with a JVM managed header used for the class pointer, identity hash code, and lock state. This indirection is the price of polymorphism and garbage collection, and it compounds when an object's fields are themselves reference types, as with string and its backing char array. Java's collections and generic methods are defined in terms of object. The type parameter t must be a reference type, so the compiler rejects primitives outright int, double, and the rest simply cannot satisfy that constraint. This is not a minor edge case, it affects every use of ArrayList, hashmap, optional, stream, and nearly every generic API in the ecosystem. Wrapper classes exist specifically to close this gap. A wrapper class is a thin, immutable object that encloses a single primitive value. Because wrappers are real classes, they satisfy generic type bounds, can be stored in collections, and can be passed to any method expecting object. The 8 wrappers byte, short, integer, long, float, double, character, and boolean are all final and live in java.lang, so they are always available without an import. 6 of the 8 wrappers simply capitalize the primitive name. The 2 exceptions are integer for int and character for char. These names predate Java and were chosen to align with established computer science vocabulary. Knowing both the primitive name and its wrapper name code is essential because you will see them mixed freely in API signatures, generic bounds, and compiler error messages. This section covers everything Java developers need to know about wrapper classes and the autoboxing mechanism. We will move from the class hierarchy through the practical API and then pull back the curtain on exactly what autoboxing compiles down to. All 6 numeric wrapper classes, byte, short, integer, long, float, and double, extend the abstract class java.lang.number, which itself extends object. Character and boolean skip number entirely and extend object directly because they represent non-numeric values. This placement of number in the hierarchy is what gives every numeric wrapper the conversion methods int value, long value, float value, and double value. Every wrapper class shares 3 guarantees. Being final means the class hierarchy terminates there, you cannot extend integer or boolean. Being immutable means that once an integer object is created, its value never changes, which also makes wrapper objects safe to cache and share. Implementing comparable means a list of integer or double can be sorted by collections.sort with no additional code. ParseInt returns a raw primitive int, while value of returns an integer object, a distinction that matters for memory and caching reasons we will cover shortly. Because integer extends number, the double value, long value, and float value methods are inherited and always available on any numeric wrapper, not just integer. The classic subtraction trick for comparison is a subtle bug. Integer.max_value minus -1 wraps around to a negative number, completely inverting the result. Integer.compare handles all edge cases correctly and should always be your default. The static arithmetic methods sum, max, and min exist specifically to be passed as method references in stream reduce operations, giving you clean, readable pipelines. The bit manipulation methods are practical tools for algorithms and low-level work without requiring any external library. The boundary constants max_value, min_value, size, and bytes are invaluable whenever you need to reason about the limits of the int type. The unsigned operations added in Java 8 let you treat the same 32 bits as an unsigned quantity, which is critical in network protocol parsing and binary data handling. Autoboxing and unboxing are entirely a compiler-level transformation. The JVM bytecode that is actually executed contains explicit calls to integer.valueof and integer.int value, nothing more exotic than that. This distinction is not academic, because boxing allocates objects and unboxing dereferences them. Code that boxes in a tight loop can produce significant garbage collection pressure that is completely invisible in the source. Knowing the compiler rewrites your code is the first step to writing wrapper-aware, performance-conscious Java. Autoboxing and unboxing look like language magic, but they are entirely compiler-generated method calls. Understanding exactly where and how the compiler inserts those calls is the foundation for writing efficient Java code that avoids unnecessary object allocation. Autoboxing is defined in Java Language Specification Section 5.1.7. Every time you assign a primitive int to an integer reference, or pass a primitive int where an integer parameter is expected, the compiler silently inserts a call to integer.value. There is no special JVM instruction, it is a plain static method call inserted by Jabac before your code ever runs. Collections cannot hold primitives, so every add of a raw int triggers autoboxing. In a loop that runs 1,000,000 times, that is 1,000,000 value of calls, each potentially allocating a new integer object on the heap. The cache covers the range -128 to 127, so values outside that range always allocate. We will quantify this cost precisely in the performance section. Unboxing is defined in JLS section 5.1.8 and is the exact mirror of autoboxing. When the compiler sees a wrapper type being assigned to a primitive variable, it inserts a call to the matching accessor int value, long value, double value, and so on. The critical danger here is that if the wrapper reference is null, that inserted method call throws a null pointer exception at runtime with no obvious call site in your source code. Compiling boxdemo with Jabac and disassembling with javac reveals exactly what the compiler produced. There is no box upcode or unbox upcode in the JVM instruction set, just invoke static for value of and invoke virtual for int value. These are completely ordinary method calls. The compiler wrote them, you did not. Once you see this in bytecode, autoboxing loses all mystery. The JLS is precise about every location where boxing and unboxing are triggered. Most developers know about assignment and collection operations, but the arithmetic and Boolean condition cases catch people off guard. Understanding the full list lets you scan any code path and immediately identify every hidden allocation site. 3 lines that look completely innocent hide 5 method calls. Lines 1 and 2 each perform one boxing operation. Line 3 performs 2 unboxing calls to extract the primitive values, executes the integer addition on those primitives, and then performs one boxing call to wrap the result back into an integer. Place this pattern inside a hot loop, and you create a continuous stream of object allocations and garbage collection pressure. Tracing the data flow for wrapper arithmetic makes the cost concrete. A primitive enters via value of and becomes a heap object. To participate in any arithmetic, that primitive must be extracted again via int value, the operation runs on the raw primitive, and then value of wraps the result once more before it can be stored in a wrapper variable. Each orange node represents a heap allocation, each green node is a pure stack operation with no allocation cost. We close this topic with 2 of the most important and most misunderstood corners of wrapper class behavior. First, the silent null pointer exception that autoboxing can hide from you. Then, a deep dive into the integer cache, why it exists, exactly how it works, and why it explains the classic 127 versus 128 puzzle. When you retrieve a value from a map whose generic type is integer and assign it directly to a primitive int, the compiler silently inserts a call to int value. If the key was never added to the map, get returns null, and calling int value on null throws a null pointer exception. The dangerous part is that the stack trace points at what looks like a harmless assignment line. There is no obvious null dereference in the source code. Nothing in this code looks wrong at first glance. But scores.get returns integer, not int. When that integer is null and you assign it to a primitive int, the compiler inserts the int value, call automatically. You cannot call a method on null, so the JVM throws null pointer exception right at that assignment line. The first fix is to keep the reference as an integer, so null is a legal value, and only unbox after an explicit null check. The second fix uses getOrDefault, introduced in Java 8, which returns the fallback value instead of null when the key is absent. Both patterns eliminate the risk entirely. Choose whichever makes your intent clearest. The integer cache is the mechanism behind the classic 127 versus 128 interview puzzle. It has tripped up developers at every level for over a decade. Understanding it precisely, not just knowing the magic number 127, is what separates a developer who avoids the bug from one who can explain and prevent it. Java programs use integers in the range 0 to 127 in virtually every non-trivial program, loop counters, array indices, status codes. Without optimization, each autoboxing operation would allocate a fresh object on the heap. The JDK designers applied the flyweight pattern, pre-allocate a fixed pool of integer objects and reuse them, rather than creating new ones for the same value repeatedly. The == operator on object references tests identity are both variables pointing at the exact same object in memory, not equality of value. Because 100 falls inside the cache range, A and B receive the same pre-existing object, so identity holds. Because 200 is outside the cache range, C and D each receive a freshly allocated object, so identity fails even though the numeric values are equal. When both variables hold a cached value, they share a single object on the heap. Identity comparison with == returns true. When both variables hold an out-of-range value, each assignment produces its own distinct object. Identity comparison returns false even though the numeric values are identical. This is why == is unreliable for integer comparisons and equals must be used instead. This is the actual OpenJDK implementation of value of, not a simplification, not a diagram. If the argument falls within the cache range, the method returns the pre-allocated object from the cache array. Otherwise it allocates a new integer on the heap. Every autoboxing operation the compiler generates calls this method, which is why the cache affects all boxing, not just explicit value of calls. The lower bound of -128 is hard-coded and cannot be changed by any configuration. The upper bound defaults to 127 but can be raised, never lowered, using the JVM property java.lang.integer.integercache.high. The math.max call enforces that the configured value cannot go below 127, so you can only extend the cache upward. In performance-sensitive applications running on known JVM flags, a wider cache can meaningfully reduce allocations. These are the rules that matter in production code. Never use == to compare integer objects unless you have verified the values are within the cache range, and even then, it is a code smell that will confuse the next developer. Always use equals. Always guard against null before unboxing. And when you see that strange identity behavior in a test or interview question, you now know exactly which mechanism is responsible. Let's recap the key takeaways from this masterclass. If this helped you, hit the like button, subscribe for a new deep dive masterclass every week, and forward this to a teammate who would find it useful. Drop your questions in the comments, I read every one. See you in the next one.